let me just recap. Right, the first thing is the feedback in general. Right, we say that any feedback system has 4 parts. One is the feed-forward, one is the sense mechanism, one is the feedback network, and other is the comparison. And I want you to really remember what is a feedback factor. Feedback factor is you get the output, then you take something from there and feedback to your input to do a subtraction, right? So it must be xf divided by y, right? So it is k. Okay, and then whether it's a positive or negative feedback, it does depends on the k also. But here we assume k is I actually should have mentioned this. Here we assume k is positive. And because k is positive, to have a negative feedback, we see that the one that input to the feed-forward system is x minus xf. Okay? And of course, the feed-forward system is what we have spent a lot of time to improve, and it is very powerful, and it is talking about y divided by z, right? You put in this much of signal, how much you get out. And this can be very large, right? After we hook up the feedback, the overall gain is going to be changed, right? And it's called the closed loop gain, which is the net output divided by the net input, right? You have a very sophisticated system, but after all, it's just a circuit. Last time we looked at the, what is that, non-inverting amplifier, and we turned out that it is just a negative feedback, remember? But at that time, we also did not think it as a negative feedback. We just think the whole thing as an amplifier, right? So this whole thing is an amplifier. And then we derived an equation. We show that the closed loop gain is just the open loop gain divided by this magic factor. I hope you memorize it. 1 plus Ka. Okay, this is very important. And why is that? You will see that. So the first insights in feedback is that with feedback, my gain is reduced. Oh, that's not good, right? Why we want to do that? We have a very high gain feed forward, and then we reduce the gain. As an engineer, you know that I give us something, I must gain something, right? And what do we gain? The first thing is the gain desensitization. So before we have the feedback, as we said, A1 probably is very large, but has a lot of variation. Anything that is large is difficult to control, right? So because, for example, the process variation, your transistor may be shorter or longer by a little bit, and then your out and GM will change, and then your gain will change. So by using feedback, as we said, the gain is no longer A1. It becomes a closed loop gain, which is, this is the closed loop gain, ACL equals to A1 divided by 1 plus Ka1, right? If the gain is really large, then 1 plus Ka1 is almost equal to Ka1, right? Because 1 is 1, Ka1 can be very large, although your K might be smaller than 1, but it won't be super small. So Ka1 is large. Then what happened? This is just 1 over K. So this is how we see that because I use this formula, as a result, my gain depends on K, not the transistor, not the amplifier A1. And K, I'm going to use something very simple, well controlled at my side to control it. For example, resistor. I can control it pretty well, right? Maybe I'm the customer. I cannot control what the vendor give me. The vendor may give me one gain of 1,000, 3,900. But as a consumer, I bought the amplifier, I hook up with this negative feedback. Then I put the right resistor ratio. I have a very good control on that. Then I may have a constant gain of 100. Okay. So, for example, the first desensitization is that it becomes independent of the load, right? I gave you a common source amplifier as an example. The gain is negative GM RD parallel RL, right? It is not just RD. And RL is something you cannot control as a vendor because your customer use it to drive a load, right? The best thing you can do is put in the specification saying that the load must be have an input impedance larger than certain value in order to have this gate, right? Then if your customer complain, the specification is like a contract, so not my problem, right? But still, you want to have your your amplifier to be versatile to many different customers. You want to make it relax the criteria, right? So with feedback, again, it becomes 1/k is independence of RL. So that is the first thing, right? Second thing is less dependence on the amplitude because the gain is not a constant as a function of the input amplitude. This is called distortion. And which makes sense. You ask it to, for example, if you ask me to do investment, I might have 100% investment gain if you give me only $100. Maybe within 1 year, I do some investment, I give you $200. But if you give me 2 million, I probably don't have this capability. I may only be able to give you 10% gain, right, as an investor. If it's 1 trillion, I don't know who can have a 100% gain, right? Because just the economic system doesn't work. Same for the amplifier. We say that we keep working in the linear regime, but when your signal is large, it's no longer linear, right? And this is called distortion. So in this case, for open loop, means I don't have feedback. The gain may be 100 at this point when your x1 is input is x1 and become x2 10 when your input is x2. Okay, so that is not good, right? Because then it has more distortion because my input signal was a very nice sine wave. And then when you output, for example, right, the input can be just as an example. My input may be like this, a very nice sine wave. But then my output may becomes this because the input is high, the gain is high, output has a smaller gain, right? I'm not output, I mean for high input, the gain is smaller, then you get this distortion. Make sense? Yeah, because when the input is at this point very small, I have a lot of gain, right? But then when I go to a high input, the gain is small, then got distorted, right? So here show you that now if we have the negative feedback, in ideal case is 1/k, then they have the same gain. But even it's not ideal. For example, let's say my k is 0.1, and then if I plug in here, you see that the gain difference change from 100 to 10 to 9 to 5, only 2x difference. So you have less distortion. Okay. So you see that I sacrifice the magnitude of the gain by having feedback, by improve the linearity, I reduce the sensitivity to the loading. Make sense? Any questions? Now the next one is that it's less frequency dependence. Let's look at it and see what happened. This is a feedback circuit we discussed earlier, right? We know that this is input, negative feedback, feed-forward, sensing, and then feedback. Right. Now, we have been assuming A1 is constant, but in reality, you already know. We already just learned earlier, right? For the common source, common gates, eventually you have a pole 1 due to the parasitic capacitor is going to be a roll-off. Remember this? So I can actually model A1 as maybe A0 divided by 1 plus maybe S divided by omega P. What is the pole of this system? How do you find it? Thank you. Set denominator 0. Then it means the pole. I mean, not pole. I mean, this is pole. Then it means what is the pole? The pole equals to negative omega P. Yeah. So it is written in the form that the pole is there already, right? So it's negative omega P. Is that okay? What is the DC gain of this circuit? Of this feed forward. This is feed forward, right? It's all talking about only A1. What's the DC gain? Is that A1? No. Say clearly. Yeah, the feed forward circuit DC gain. The feed forward is A1. So when frequency is 0, what is that? A0. Yeah, A0. Right. So I can draw this circuit, the Bode plot as this. This is log frequency, and this is 20 log A. Let me don't do this. I will just say the gain. You'll see Y later. Then it will be something like this. Correct? And this is negative 20 dB per decade. And this is, what is this? Omega P, right? And this is A0. This is the A1 that I have, right? I bought it. Then I hook up in the feedback circuit. How will it look like? Very good. So he said lower gain and wider bandwidth, right? Did you learn that before or you guess? Huh? Oh, you already know that, you learned that, right? But you also will guess, you always think that first, engineer are not stupid. If I make it lower, probably we want to have a wider bandwidth, right? So let's see why. So let's look at the closed loop gain. What is the closed loop gain again? I think you should be able to memorize the equation already. 1 plus Ka1 if K is positive. Yeah, very good, right? So then I want to know its frequency response. I'm going to substitute A1 to it. So the top is A0 divided by 1 plus S over omega P. And then K times A0 divided by 1 plus S divided by omega P. All I have done just substitute A1 with this equation to here. Okay? So then just go through the regular math. I try to remove 1 plus S over omega P. This is not a good way, but still just if we don't have insights, that is what I will do. Then this becomes this, right? Correct? Denominator and numerator multiply by 1 plus omega P. Then this is A0. Then Ka0 is by itself. Then the whole thing becomes 1 plus S divided by omega P, right? But this does not give me any insight. I want to make it in a form like this so that I can find the pole right away and also the DC gain, right? Which is not too difficult. So how would I do? I want to divide the whole thing so that I have 1 plus S divided by something. So it looks like I need to divide it by 1 plus Ka1 for both numerator and denominator. So the numerator becomes A0 divided by 1 plus Ka0, not Ka1, Ka0. And then denominator is what? 1 plus Ka0 divided by 1 plus Ka0 is 1, right? And then the S term is this, omega B times 1 plus Ka0, right? It's just a change of the variable, right? Divided by 1 plus Ka0, A0 becomes this. And then this whole thing divided by 1 plus K0. 1 plus K0 divided by 1 plus K0 is 1. S divided by omega P divided by 1 plus K0 is this one, right? So based on this, now can you tell me what is the pole of this closed loop gain? Yeah, thank you. Although it's trivial, thanks for keep answering my question. Negative omega P times 1 plus K0. Because we already know that if you write it as 1 plus K divided by something, this something must be the pole, right? Or you just set the denominator to 0. It's up to you, right? What is the DC gain? When DC gain means S equal to what? It's a 0. Yeah. Becomes A0 divided by 1 plus Ka0. Because it means I will set S equal to 0, right? Then this is 1, right? Or again, in this form, I know the top one is the DC gain, right? And then is this surprising? You saw this before. We already been doing this, right? We say the gain, closed loop gain is A1 divided by 1 plus Ka1. At that time, we did not think about frequency response. Isn't that just the same? If there's no frequency response, the DC gain should be reduced by 1 plus K1. So everything makes sense, right? So then in the graph, we will see that this is reduced, and then this is increased. Okay, so here becomes omega p times 1 plus k A0, and this becomes A0 divided by 1 plus k A0. Okay, so what you said was correct, right? Reduce the gain, increase the bandwidth. But particularly if you look at the product of the bandwidth and the gain, before it was A0 times omega p. Before feedback, this is no feedback, correct? But now with feedback, what is that? It is A0 divided by 1 plus KA0 as the gain. But the bandwidth becomes omega b times 1 plus KA0 as the bandwidth. They are the same, right? This is with feedback, right? So this is the so-called gain with, not this one, gain bandwidth product is constant. Okay, it's just a very simple concept. It's just like conservation of energy, something like that, right? But this is the product is conserved. Instead of potential energy plus kinetic energy is the same for the ball without friction. Okay, so what do you learn here? This one is like you already learned, so you are done. But if not, this should be something very clear, very simple to you, right? Very obvious to you because you're an electrical engineer. Lower the gain, product is larger. And remember, it's talking about this product, right? So this is log scale, so you need to be careful when you talk about the area. There's some relationship, right? But the point is the product is conserved. Okay, any question? So good. Another good thing about feedback is I increase the bandwidth. Now think about that. If you have a transistor, you have a common source amplifier we discussed earlier. This first pole is due to what? The parasitic capacitor, right? Maybe the Mueller cap, right? I forgot which one. 1 over Rs CGS plus CGD times 1 minus A. And you see that you cannot do anything, right? Because I only have this transistor, I do the I create the amplifier, unless I change to another technology or whatever. But maybe I don't need such a high gain. Then let me do a feedback. Then I increase the bandwidth. Even originally, this parasitic capacitor is hurting my bandwidth. But now I can reduce the gain and have a larger bandwidth for the application. Okay. So now I want to go to another thing